Okay, welcome everyone. My name is John Gibbons. I'm with AT&T Labs, work a lot with Tom, and I'm part of the program for our Universal CPE program, which is a white box program to deliver enterprise services to enterprise customers. So I just want to take you through what we've done in OCP for the spec and where we're at. So I have a colleague of mine here, Dustin Grant, who's actually going to talk about a little more of the detail. So anyway, let's just jump into it. So we brought, I think it was started in last May, we brought this Universal CPE spec. Again, I'll talk a little bit more about the box as we get into it, but it's essentially an x86 platform with merchant silicon that would go on a customer prem location, store, a bank, whatever it may be, where we provide managed services to those customers. And then we can virtualize the network functions. So the router can now be a virtual router running on x86. It could be a firewall, a Fortinet firewall, for example. So we'll have a catalog, or we already do today, a catalog of different network functions that run on this box. So it's really primarily an x86 forwarding. So a lot of the packet forwarding happens on the x86. And I'll talk about, we do have some merchant silicon to offload some of the traffic. But anyway, we started this work last May. We got approved and ratified by OCP, I think, in January. So it's a ratified spec. It's actually the high-level design. So we like to announce today that we have Silicon Limited is an ODM, and Intel have agreed to make this the lower level spec, initially the board design, available to the OCP community. So it'll both be the high level and the actual detailed board design. So they're going to work to have something in draft format by middle of this year, and then have the final draft or the final certified spec by the end of 2018. So I got, I think he's here. Elad is Senior VP with Silicom. So Elad, if you want to say a few words quick, I can give you the mic. I mean, it's... So it's been a good partnership. We've worked along with Intel. Intel's here with us as well. And yeah, go ahead.
Okay, so first of all, thank you.
Yep.
We've been working with both AT&T and Intel to create this and make it come to life, and we hope that in the near future we'll come with more and more designs both for the low end and for the high end to complete the picture, to allow anybody who wants to build a universal CPE solution together with us, together with AT&T and with Intel, to have quite a variety and quite a lot of options in order to create really a full solution for whomever wants to deploy this.
Okay, well, thanks a lot. All right, so I just want to go into the architecture of the spec from a high level, what it is. It's really an Intel-based x86 CPU. Now, we have 4 models. Obviously, in the enterprise, you could have very small sites. Picture a retail store in a mall. They don't have a lot of needs. So we have a very low-end box with this based on a Denverton CPU. But then as you move up, we have a small, medium, and large that are Xeon class, Broadwell DE, and eventually Skylake D-based systems. Again, these are relatively high core counts because a lot of the packet, the VMs that run these things are going to be running on top, and we'll be doing packet forwarding through the x86. But what makes this different than a typical server is we've integrated a layer 2, layer 3 switch at the bottom, which is either a Marvell on the very low end, and then it's a Broadcom-based switch on the larger platforms, and all the switching can be done locally. So LAN-to-LAN switching gets done locally, say, LAN port 1 to 3, that does not have to go up and take x86 cycles. We can do the switching locally. And eventually, with the flexibility, if you had traffic that doesn't need to go up to a VM for processing, you can switch that LAN to WAN locally. So in reality, this is a premise-based. It goes to the customer site, and we're going to be able to integrate multiple network functions. And eventually, we want to put other functions on this. It could be AI-based functions, IoT-based functions. It doesn't have to be traditional network functions. Anything that can run on a server would actually run, on this platform. This is the overall design. We've got dual power options. Not every platform needs dual power. But we also integrated a BMC in there too for remote management so that we can get in. We're using an LTE external modem for our operations to get in to manage it. You can build a modem inside this if you want. Dustin can talk about that. If you want an internal modem, that's fine. And what's really important about the design is this modular daughter card. So when we look at enterprise, we want to develop something that's Ethernet based, But there's a lot of legacy things out there. For example, so you might have legacy voice ports. There's a PBX that you want to hook into the router and transport over the IP network. So by having this modular slot, we're able to support some of this legacy with a next generation box. And then conversely to that, maybe in the future, it could be an AI module. It could be IoT-based modules, extra LAN ports. So having some modularity in this platform was very important to make it more flexible. So with that, I'm going to have Dustin come up. He's going to take you through a little more detail on each of the different sizes from the extra small up to the large and what they look like. There you go. Yeah.
Hi, everybody. As John mentioned, my name's Dustin Grant, working at AT&T. So we'll go through the sizes and some kind of mock-up pretty close to the final design of the actual universal CPE. So all the CPU, the memory, the storage, this can obviously be reconfigurable based on your requirements, but this is our reference kind of for our configuration, for our needs. So for what we call the extra small, it's a 4-core Denver Tennessee 3558, 8 gigs of RAM, 64 gigs of storage. We have a small Marvell switch to do the local LAN switching, and then SFP and RJ45 for the WAN ports. You can see from a hardware perspective kind of what the overall chassis looks like. And you'll see here the modular daughter card that John spoke about. So this would be where we would put an expansion port for whatever the need is, more Ethernet ports, or more likely like a T1, FXS, those types of ports. So you'll see that a lot of the overall design is very similar across all the platforms. It just kind of scales up with more ports, more memory, more storage, more CPU as we go up the stack. So when we go to what we call the small, we switch from an Atom to a Xeon D class CPU, this being a 4-core Xeon D CPU. So it's a higher performing, has hyper-threading, and then more memory, more storage. And we switch to a higher end Broadcom Hurricane 3 switch for doing the local switching. It also allows us to do higher performance and deeper packet inspection for layer 3 and layer 4 forwarding if we want to do that in hardware for some use cases. And so this mock-up here is actually not very close to the final. What you're going to see is this module slot is going to look and be compatible with this one here. So we were able to actually kind of move things around and make room to fit that module slot and expand this board over. So this will change in the final design, but we don't have a mock-up of a pretty looking mock-up of it right now. For what we call the medium, it's essentially exactly the same as the small. It's just we're just upgrading the CPU and the memory and the storage. But everything else is identical. And again, the same thing applies with the module slot. So that module slot will still be there for the expansion. The other modules actually that I haven't mentioned yet is there's quite a bit of internal expansion as well. So we have M.2 slots. There's 2 M.2 slots, a mini PCIe slot. There's 2 USB slots, and this gives us a lot of flexibility in adding things like LTE modems, IoT type, Bluetooth type modems, and then even as you've probably seen at the show here, there's some like M.2 based FPGA and AI chips starting to come out. So for various different use cases, you can populate those into these internal slots. For the large, we really, this one actually, we've changed the design on this one as well because we wanted to add more modules. So this design is actually going to change from a 1U design to a 2U design. And what you're going to see is on the top is where there's going to be module slots. So we're going to have 3 module slots that can be populated. And we're going to take up the entire bottom with switch ports. So we're going to, instead of seeing 16 RJ45 ports, you're going to see 32 RJ45s plus the 8 SFP. So this entire bottom here will be populated with with switch ports, and then a second RU with the module slots. So again, we don't have the updated diagram, but that's what you'll see later this year when the design comes out. And again, this one's just kind of upgrading, and this is where we introduce a secondary power supply as well. So on the small, it's just a single power supply. The medium, it's an optional redundant power supply, but in here it's going to be a dual redundant power supply for all the platforms. So what's next? So besides the platforms that we just showed you, what's next in the pipeline to work on with OCP? So we want to work on standardizing these network modules. So some of you may have just came from the OCP3 NIC session. We would like to try and leverage that ecosystem of modules to be able to put into the UCPE. The challenge, though, is that the OCP NIC is really designed for high-end servers, so it's really only PCIe. If we can work with just PCIe for all our expansion needs, like for example, something like an LTE modem is typically USB attached. If you could do it with PCIe, but it adds cost because you have to bring in more controllers. So we need to work through if we can work with just PCIe for the backplane connection, or if we need to be able to have other types of bus connectivity into the host. So that's kind of the goal, is to at the very least leverage the form factor of the OCP NIC, and if not the entire module ecosystem. Another area of attention is the OpenBMC. So the OpenBMC is starting to take off within OCP and the Linux Foundation. We'd like to contribute our use cases and our requirements into that project as well. And then finally, another hardware device that we're going to start a new specification on is the SIAD. This is a cell-side access device, so I'm going to let John take over from here and talk about that device. Is there any questions so far for me? Oh, go ahead.
Yeah, so I think the question was the use cases for small through large, so extra small through large. So we see a lot of different customers out there. Some are very small. They don't need a lot of virtual machines. They don't have high bandwidth needs, so the small works fine. They may want to, maybe they have an internet connection at their site and they want to run a router in the base and then maybe a firewall like a Fortinet to protect the site. So you don't need a big box like the large. But a lot of customers typically have a lot of large sites, right, that are data centers or campus locations. They're going to need like 10 gig type WAN access. That's where the large would come into play, and then the small and medium just kind of fit in between. So one of the things we see with this universal CPE is there's two components now. Usually in a traditional network, you'd pick your device based on the throughput you need. But now this is a compute platform, so it's throughput, but it also may mean the applications you want to run on it. So you may only have 20, 30 meg access into the site, but maybe you would need a larger box because you want to put different applications running on it. So it's kind of a combination of a network and a server together. Okay.
Question is, what is dying gasp? That's a good question. So dying gasp is just basically the ability for the system to reserve some power in a capacitor, and when it detects that power is lost, it can send an alarm back to our management center and say, hey, I've lost power. And this is a really one of the biggest requests from our operations team, because they say it saves them a tremendous amount of time when troubleshooting issues. Otherwise, all they see is a device has gone down. They don't know why, so they're assuming a circuit's down, the device has failed, and so knowing that the power has been lost is a very useful piece of information. Yep.
Is the MEC? The question is it part of the MEC architecture? No. Well, No, it's OCP right now. We do have a lot of representation at AT&T and MEC, so actually talking to our focal point on that. So we're actually looking to potentially do some demos at the next MEC event and look at that. Right now, not, but eventually we're talking about it as well. Yep. All right, I know we only have a few minutes left. I want to take you through, so we're going to switch topics. Yep. So Dustin introduced the SIAD. That was not working. All right. Let's click the laptop. Oh, there we go. That switched? Okay. All right, so the SIAD is just an AT&T name, Smart Integrated Access Device. And what it is today, it's a traditional router that sits at our cell sites. I assume most mobile providers do this as well. And really what it does is aggregates the base station. So there's multiple base stations. You have LTE, you're going to have your UMTS legacy, eventually 5G in the near future. And so this is a router that aggregates those interfaces. It provides routing back in toward the packet core network. And it does traffic management, obviously. So you're doing class of service, you're shaping it. You might have 10 gig interfaces coming in, but maybe your WAN is only 1 gig. So it does a lot of the functions a traditional router does today. We as AT&T, as we're moving toward 5G, we're going to have to upgrade that infrastructure at the cell sites for the more bandwidth that'll be coming out. So this was really good timing. So we wanted to bring a new spec to focus on a cell site router, essentially, or a SIAD, into OCP and to get that certified. Janet Pang is here. She's a peer of mine in AT&T, and she's leading that effort. So this will not be led by Dustin and I, but Janet, her team brought that to the Telecom Working Group, I think 2 weeks ago during our monthly conference call. There was a lot of good feedback and interest in that. So that's our next thing as far as the routing functions. A couple little things on the SIAD. So it's a different architecture than the UCPE. One of the key things, it's got to be hardened. Cell sites are not, data centers are perfect conditions environmentally. So it's going to have different temperature range. It's going to have to be relatively small. There's not always a lot of space at a cell site. And I'm not going to go through all this stuff, but a couple different things is the ability to have hot swappable fans and power supply is very important. We don't want to have to switch this box out if we have a failed fan. We want to be able to swap it out, same with a power supply. There's a lot of timing requirements for cell sites, for the equipment that's at the cell sites, whether that's supporting a local GPS and bringing that in, or supporting a network-based like a 1588 V2 timing source coming through that and handing that out to the elements at the site. We also want to scale this up. Obviously, cell sites are not going to jump to 100 gig access, but when you look at some of these architectures in the metro areas, you may have these cell sites or these sites aggregating multiple cell sites into it, and then you're going to have a big uplink to the core network. So it will have some 10 gig, 100 gig ports on it, and again, only used in this limited areas. But the sweet spot's going to be the 10G, the 1 gig access from cell sites back into the network. Most of it's going to be SFP-based ports. A lot of security too. We're looking at MACsec-based security. We want to put a BMC for remote access. We want to eliminate as many truck rolls to these sites as possible. So even if the site is down, if you have a neighboring cell site, you could still come in through an LTE modem to your BMC to troubleshoot the problem, avoid sending someone to that site, and hopefully get the site back up online much quicker. It will have an x86 CPU for control plane purposes, but as the UCPE that I just talked about was forwarding a lot of the traffic with x86, this will have a Broadcom Qumran chip in it, and it'll be hardware forwarding based. So that's a big difference to this to get the throughput if you want to go up to 100 gig. So really quick, this is kind of a block diagram. This was, again, presented by Janet's team 2 weeks ago, what the block diagram. So you can see the Qumran in the middle will be the heart of the forwarding plane for this. You have the timing support on the right, and then you have your control plane running on the Intel CPU, the 4-core, 16 gig of RAM and 128 gig of SSD. So this is just starting, so we're looking for a lot of input and collaboration on this, and we'll do, we can do that, through the monthly calls as well as the mailing list. I think there was a lot of interest on the first call, obviously, for any providers that are in the mobile space, and there may be other applications outside of the mobile space for a box like this. So I think we got a few minutes left. I'll open it up for any questions on anything we covered here today.
I think we're out. So
okay.
Maybe we can get you to go out And
Sure.
we'll have questions, can
Yep.
can catch up with John and maybe Janet too.
Yeah.
Just outside the door.
Yep,
And we'll
okay.
go ahead and transition
Sure.
to the next talk.
Okay, great.
Thank you.
Okay. Yep, thank you. Thank you.